Today we are going to learn about functions, but it's going to be a little bit different from the functions that we saw and worked on in Cal 1 last semester. So let's take a look here. In Cal 1, we have seen a lot of this function fx. We have seen this a lot, and we perform many kinds of computations when it comes to this fx. We find limits, we find derivative, we find integration of fx. So that's what happened in Cal 1. And let's take a look at this fx. When we see fx, we know right away that this x is considered to be the input of this function. This x is going to get passed through this function called f, and in the end we have this fx coming out of this function. Alright, so when you see it as a process like this, you can consider x to be the input of this function. Alright, let's make a note here. X can be considered as input. And then this function is called f, is going to do something with this x, and in the end it changes its value to fx, and this is considered to be the output of this function. Sometimes this fx is called image of x. So make a note right here, fx, image of x. It's like what happens after we change x into something else. Alright, so let's take a look at an example here. Fx equal to x squared plus 2. So here you can put x, any values of x in, like x equal to 0, and then you get, for example, x equal to 0, f0, you get 2. So right here, this x is equal to 0, and what you see 2 right here is the output. So 0 here is the input, and 2 here is the output, and also the image of this x equal to 0. Right? So I was talking about this kind of process, input and output. And also here I want you to make a note about this x and fx. What you see x right here is a scalar. Alright? So you put in some x value, like x equal to 0, x equal to 2, x equal to 4. And they all are going to give different value of fx. So if I put 0 right here, I get 2. What if I put x equal to 2? Then I get 4 plus 2, that becomes 6. Right? And as you can see here, the output that I got from this function is also a scalar. So also a scalar. Alright, now let me ask you just two interesting questions. What do we call the set of points that represents all possible values of x? Set of all possible values of x? Well, I think some of you know that it's called domain set. What about the set of all possible value of fx? Well, all possible value of the outputs, that's going to be the range set, right? Range and domain. Now let's move to what we are going to learn today. Now today is going to be a little bit different, but in a lot of way, it's quite the same. Today we are going to learn about this function r of t. Okay, and let's make a box around that. So last semester it's fx, today it's about r of t. Looking at this form, you know right away, t is going to be considered as the input, just like fx, and this function is called r. And in the end, we get this output from this function, and it's called r of t. And just like fx, it's going to be the same process, t as input, r of t here as output, and what you have right here, r of t, is the image of t. Image of t Alright, and t right here also a scalar. You can put t equal to 0, t equal to 5, t equal to 10, t equal to 100. That's up to you. And it's going to get passes through this function r, and in the end we get this r of t. Now here's the difference between today's function and last semester function. R of t here is going to be vector. So make a note here, R of t is going to be vector, and that is the main difference. Alright, since this is vector, I am going to add this sign, vector sign, above this R. Same here, and same here, to remind ourselves that the output of this function is a vector. And that's why in this slide you have this this title right here, up here, called vector valued function. Vector valued function. Sometimes we call this short as vector functions. This vector right here indicates that the output of these functions have to be vector. So the keyword is right here. You are going to get a vector out of this function. So make a note right here, vector as output of functions. Right? If the output is vector, we call it vector functions. What about the output is scalar, like this, fx? The output of scalar. The output is scalar. Then you can choose to call this fx scalar valued function, but it's not necessary. We usually call this scalar function as regular function. All right. So you can call this scalar function if you want, to make it more specific. Scalar function or regular function, and this is vector function. Alright, now that you know the main difference between today's function and the functions we had in Cal 1, let's take a look at the more details of this vector function. Since we have learned that vector functions have vector as output, then there must be something special about this output of this these functions. So this R of t are going to have components. So the key things is right here. R of t has components. Well, they are vectors, right? They must have components. So R of t can have I and j components in 2D. Alright, I and j components in 2D. And if you work in 3D, it must have I, j, and k components. Alright. And not just that. What is important about this vector R of t is that it has components that depends on t. Right? So add more comments here. Has components that depend on t. Very important. It means that if you feed in different values of t, then the components are going to be different, and you are going to get different vectors. And that's why we need to display these vector functions as what you can see in this box down here. So what you see right here is the regular form of vector functions. Since this is vector functions, I am going to add this vector sign right here. And of course, we have t as input. And t here is a scalar. You can view t as time. Time equal to 0, you get one vector. Time equal to 1, get another vector. Scalar. Alright. And since this is vector functions, the output has to be vector. So on the right hand side, you see this output right here, and it has all these components. Definitely vector. So this is definitely vector, and it's the output from this function. The output, as I told you before, the output must have components that depends on t. So let's take a look at the components of this R of t. As you can see here, we have I component, J component, and K component. This means that we are working on 3D space. And let's take a look at the detail of each component. So here you have this f of t as the value for the I component, g of t for the j component, and h of t for the k component. As you can see here, they use different functions for each component. What this means is that each component are going to change differently and independently when it comes to different values of t. So make a note here. Each component of RT, each component of this vector R of t is going to change, and here's the keyword, differently and independently. Differently and independently with respect to time or t. It means that each component of RT doesn't have to change in the same way as the other components. So let's take a look here. For I component, the change can be described by this function f of t, right? And it's different from the change in the j component, which is explained by a different function of gt. And same for the last component of k, explained by another function. Now let's take a look how we can make use of these vector valued functions when it comes to applications. Most of the time that we see vector functions, they are used to describe lines or curves in the 3D space. So let's take a look at an example here. In this example, we are going to use the vector functions to explain the curve in three-dimensional space. Curve in three-dimensional space, 3D space. Well, let me tell you something. We have seen the use of these vector functions before when we learned how to create a straight line in 3D. If you can remember, straight line in 3D. In 3D, where we use this formula, R of t equal to vector R0 plus t vector v. This is one version of this vector functions, and we use that for the straight line. Here we have more freedom, and in this example it's going to be curve, not a straight line. So what you see in this box right here is the vector function that describes the curve that you see in the figure below. Well, it's kind of hard to associate this kind of equation to curve in space. So let's try to do some visualizing in our head to connect them together, right? So here, what do we have here? We have vector equations, vector functions, and we have this t as the input, and then each component is going to change independently. So we have ft for the I component as cosine t, and gt for the j component as sine t, and ht as just t for the last component. Okay. Now let's try to look at this this function without considering the k component. So why don't we focus on the first two components here and try to look at this in the space. Okay? Now, let's make a note here. ij component only. I and j component. Alright, let me fix that. I and j component only. I and j component Alright, so let's take a look here. What happens when we input t equal to 0 to this vector function r of t? So r0, let's put 0 into this function and we get the first component to be cosine 0, and cosine 0 is 1, and we have this I. Alright, now next one, sine t, sine 0, we have 0j, and for now we neglect the last component, so we don't talk about k here. So this is a position vector, alright, and we translate this into coordinates, and we get this coordinate of 1 and 0. Let's put this point in the space. So x equal to 1 and y equal to 0, and for now we work on xy plane, because z doesn't matter at this point. So let's put x equal to 0, x equal to 1 and y equal to 0. It's right here. Alright, this is the starting point at t equal to 0. Let's try a few more. What happens to this vector function when t equal to pi over 4? Then the first component would be cosine pi over 4. That is going to be 1 over square root of 2, I, plus sine of pi over 4. That's going to be, well, same thing, 1 over square root of 2j. This is position vector, and we translate this into coordinate in space, and that's become 1 over square root of 2, 1 over square root of 2, and it's going to appear maybe around here. Alright, at this point this is 45 degrees or pi over 4 on xy plane. Now let's try two more. What happens to this vector function at t equal to pi over 2 or 90 degrees? Here we have cosine 90 degrees, that's going to be 0, I plus 1j. Change this to coordinate in space, we get 0 and 1. Alright, 0, x0, and y equal to 1, it's going to be here. Alright, I want you to see the flow of this, well, the movement of this point, of these points. Starting from here, it's going to move in this direction, right? Starting to circle around the origin. Now let's try more. The last one, pi. Cosine pi, that's going to be minus 1, I. Sine of pi, that's 0j. This corresponds to the coordinate of minus 1 and 0, and it's going to be back here. Now let's extend the x-axis. Alright, it's going to be here. X equal to minus 1 and y equal to 0. So we can see that the point starts to move in circle, right? Starting from here to pi over 2, and then continues around in circle, and in the end it's going to return to the original point. Alright, so we are looking at this flow, and the flow that we see right here is on xy plane. Flow on xy plane, and the reason that is on xy plane because we don't consider the k component here. Make a note here that don't consider z or k component here. Now, so we see this kind of flow going on, and it's circling around this same center. Well, it comes out to this full vector. We cannot just leave the last component away. We need to consider it too. So now let's consider this t of k. So as you can see here, ht equal to t, which means that as t increases, the k component is going to increase as well. So let's make a note here. As t increases, the k component increase as well, which means that our curve is going to get lift up higher and higher and higher as t increases. So we are going to start at t equal to 0, and it's going to be here, height of 0, right? Starting at tk, when t equal to 0, we get 0k, so we start here. But when t increases, it's going to circle around the origin, but the height is going to lift up this curve, and as t increases, it's going to get higher, higher, and higher. Alright, I'm gonna try my best to make this happen. Alright. So in the end, you have this this curve, and this kind of curve we call the helix. So it's a curve that circles around the z-axis. Alright, so in this example, you see one use of the vector functions, and it can show you it can explain the curve in the space. Alright, let me make this look a little bit better. And there you go. Same as the vector we have up here in the slide. Now, let's move to the next one. In the next one, it's about the calculus of vector functions. So here we know the idea and the concept of this vector functions, r of t equal to, well, ft I, well, we have components here, right? gt j and ht k. And we don't just want to use it, we want to perform calculation on it. We want to do a lot of things with this, and including calculus. Here I want to keep things simple. So let's make a note here. When it comes to vector functions and the calculations that are associated with it, it's all about performing the calculation on each component separately and while keeping the vector form. So make a note here, it's quite long. So when it comes to the calculus or the calculation of vector functions, we perform calculation, all right, on each component separately. So this is the key word. You perform the calculation separately. But not just that, in the end, you still need to keep the vector form while keeping the vector form. So if you perform any calculations, in the end it has to be vectors, just like before. Now, what kind of calculations are we talking about? We are talking about limits. Well, limits, differentiation, and integration. All right. So if you want to find the limits of this RT, all you need to do is to find the limits of each component separately, but in the end it has to come out as vector. All right. Same for differentiation. If you want to find the first derivative of this RT, then you find the first derivative of each component separately, and in the end keep the vector form. Same for integration. All right. So I give you this tip right here. That's all you need to know when it comes to the calculus of these vector functions. So let's take a look at some definitions here. Here, the first one at the top is about the derivative. So let's assume that you have this vector function r of t, and as you can see here, you have all these components. Well, fti, gtk, and so on. And then you want to find the first derivative of this. So here you want to find this rt prime. You want to find this rt prime, and this is first derivative. Now that our functions look a little bit different, the calculation is going to be different too. So here we stick with the one concept, perform the calculation separately on each component. So we are going to diff this function with respect to the variable that we have, right? With respect to t. Of course, we have to do this with respect to t because this is, it's expressed in terms of t, right? So that when it comes to calculation, diff f with respect to t separately, diff g with respect to t separately, and diff h with respect to t separately, and in the end you keep this vector form. Alright, r of t starts as vector and ends as vector here after finding the first derivative, and you perform the calculation. Here is the differentiation separately, one by one. Alright, so that is the differentiation of vector function. Now what about the integration? So let's take a look here. We have the same vector function of rt and same components f, g, and h. Here we want to find definite integration of this rt. So here, well, in Cal 1 we have something like this, fx dx, integrate of that starting from x equal to a, ends at x equal to b. But that is too easy. Here we want something that is more challenging, so we are going to move to this vector function of rt. Now, things look a little bit different, but when it comes to integration, it has to be performed on the input variable, which is t, right? Input variable, make it here input variable, and that's why we need to perform the integration with respect to t, just like we did with the differentiation, diff with respect to t. And here what you see here, a, this t equal to a, not x, and same here, t equal to b. And just like before, we stick with one concept, perform this calculation on each component separately. Alright, let's see if it's true. So here we perform the integration of each component. Now here we see this component I, so we perform this integration on f, and then same thing, integrate from t equal to a to b, and then we do the same calculation, but for this j component we work on g instead, and the last one we work on h function, which represents the change in k component. So as we can see here, we work on each component separately, but in the end we keep this vector form. Oh, what happened? I'm sorry. But in the end we keep this vector form, I, j, and k. Alright, so we start here with rt as a vector. After we integrate rt, we still get a vector. Alright, same with the differentiation. Start with a vector and ends with a vector. Okay, you might need to make a note here that r prime t is a vector, and this integral also vector. Well, in the end it's just the same concept. Do the calculations 3 times, one for each component. Now let's take a look at the example down here we have this vector function r of t equal to cosine t, sine t, and t for the last component. Well, this is the same as the helix that we saw earlier. So what is important about this example is that they want us to find a limit on this function when t approaches where? T approaches pi over 4. And just like before, calculations on each component. So this limit goes to the first component, and then we get this first limit. Alright, this limit goes to the second component, and then we get the second limit. And the last component, same here, and we get this. And it turns out that in this case we just need to do the direct substitution in order to get the value. So cosine t when t approaches pi over 4, that is 1 over square root of 2. Same here with the sine of t when t approaches pi over 4, we get 1 over square root of 2. And of course, limit of t when t approaches pi over 4, you get pi over 4. Well, in the end, it's just about applying limits. Applying limits to each component. And as you can see here, in the end, we still have this vector after the calculation. Alright, let's move to the next slide. Well, in this slide is about the differentiation rules for vector functions. Just like in Cal 1, when it comes to differentiations, we have many rules. So let's take a quick look through here. It's going to be quite similar, except some operation that is a little bit different. So here, differentiation rules for vector functions. So we are talking about this r of t. Well, in this case, they use u of t, so let's use that. So here, vector functions, you can use u of t to represent that. So when it comes to differentiation of vector functions and you have constant, then after you diff that, you get 0. So you might want to make a note here: diff constant, you get 0. Alright. Now it's different from number 2 in the way that in number 2 we have constant in front of a function. Right? Here we have constant in front of u. If you diff this product in this case, all you need to do is to take c out. Right? So here c just comes outside and you apply the differentiation directly to u. So in the end it's going to be this, equal to c dut by dt. Right? I still see many of you make a mistake, right? Because you mixed up between 1 and 2. Sometimes you see this this number 2 and then you assume it to be 0. It's different between 1 and 2, right? 1 is just constant alone, right? Keep in mind that diff constant alone, you get 0. But if that constant is with something else, you need to keep it. There is nothing much to talk about some rule. If you have two functions, vector functions, added together, and you want to diff the sum of these two, all you need to do is to apply the differentiation to each one of them. Or you can add them first and then diff in the end. It's up to you. So you can distribute this differentiation to each one of them, and you get this diff u and derivative of v. Same with the difference rule. Vector function u minus vector function v, you can perform the difference here first and then apply the diff, or you can distribute this diff to each one of them. You can do that too, and you get this. Now, the one that is a little bit different here is the product rule. Why? Because when it comes to vector, we have two kinds of products. All right. When we worked on scalar, we only have one formula for product rule, which is this is how I remember front diff back minus plus back diff front, right? For fx, I'm going to make a note here for fx. Okay, let me write it like this. Fx and times with gx, and if you want to find the derivative of this with respect to x, right, this is going to be front and diff back plus back diff front. Okay, diff front, that is f prime x. Well, here we have two kinds of products. We have dot products and cross products, but it turns out that we use the same concept, right? It's going to be front diff back plus back diff front, but the operation is going to depend on the kind of product. So let's take a look here. We have product of two vector functions here. So let's take a look at the result of this differentiation, the product rule. So here we have front, right, u diff back diff v plus back v diff front. All right, same with the cross product. Front here diff back plus back diff front. And the operation between, well, u and v, it depends on dot and cross. Here we work on dot for 5, so we have dot between these two. And for cross product, you have cross. So in the end, it's the same concept, all right? And of course, you can apply the chain rule. Now, let's try some calculations on these examples, all right? So what do we have here in the first example? We have this r of t. Let me write this again. R of t equal to 2 ln of t plus 1 I, that is the first component, and we have the second component t squared j plus e to the power of minus t k hat. Okay, that is what we have in the beginning, and we want to find this. Well, the first derivative of r with respect to t, you can write it like this: drt by dt at t equal to 1. So let's diff this. We want to perform differentiation of this r of t. So d by dt. So we are going to apply this to each component separately. So the first thing we are going to do here is to diff this d by dt of the first component 2 ln t plus 1 I plus, now we diff this separately again, dt, d by dt of t squared j plus, again, diff with respect to t of e to the power of minus t k hat. After this, it's quite easy. All we need to do is to perform the differentiation 3 times. We need to diff 2 ln t plus 1, and we know this is going to come out to be 2 over t plus 1. Alright, and this is the first component, I. Now we diff t squared, we know it's 2t. That's j. And the last one, we diff exponential, we still get the exponential back, but we perform the chain rule with the power of minus t, so we get minus 1 in front, minus 1 right here. So we have this k hat right here. What about I change this to minus? This looks better. So what you see right here, this is r prime of t, the first derivative of this vector function rt. So let's put the box around it. Alright. Okay, and the next thing we need to do is to find this first derivative at t equal to 1. So let's put t equal to 1 in. R prime of t equal to 1, so that's going to be 2 over 2. That's going to be I, right? 1 times 2, we get 2j. Minus, well, we put 1 in, so we are going to get 1 over e k hat. Alright, and that is the answer for the first example. As you can see here, when it comes to the calculus of this vector functions, is the same as what we did in Cal 1, except that we did that 3 times, right? For first component, the first time, second time for the second component, and of course for the k component. Okay, let's move to next example. This example is about finding the integration of vector function. Let's make a note here. First example is differentiation of RT. For this one is definite integration of RT. Alright, let's do that. Here we have this RT equal to, okay, let me write it again. Cosine of t, that's the first component, I, and plus j, alright, and minus 2tk. Right, and we want to perform the integration here. Integrate this r of t with respect to t, of course, starting at t equal to 0 and ends at t equal to pi. So we are going to do this, perform the integration of this whole thing with respect to t, and t starts at 0, t ends at pi. And just like before, we are going to distribute this integration into each component. So let's start with the first one. Integrate t equal to 0 to pi of cosine t with respect to t, and that is the first component. Don't forget to keep the vector form. Every year I see some of you like working on something like this, and all of a sudden I, j, and k is gone, right? So keep it. Now next component, same thing, t equal to 0 and to pi, and we integrate 1 here, dt, j, minus last component, integrate, same thing, t equal to 0 to pi of 2t, and here with respect to t, and here for k component. Now we integrate cosine t. We all know that it's going to be sine t, and since this is definite integral, you have to calculate this at 2 values, starting point 0 and pi, and that is the first component. Now next one, integrate 1, you get t, and 2 values, 0 and pi, j component, and last one, integrate of 2t, you get, well, t squared over 2, right? 2t become t squared over 2, and 2 right here cancel, and you are supposed to evaluate this at starting point 0 and pi, and here on the k component. Now let's evaluate this. Sine pi minus sine 0, I, plus pi minus 0, j, minus pi square minus 0 square, k hat. Alright, here sine pi we get 0, and these two are 0, so we have 0i. Alright, plus pi j minus pi square k hat. You can leave your answer like this in ijk components, or you can use this representation of vector, which is the angled parenthesis 0, pi, and minus pi squared. Alright, and keep in mind that this is equal to the integration, definite integration of rt, vector function rt, with respect to t, starting from t equal to 0 and ends at t equal to pi.